So hello everybody, I'm very happy to have you here. Thank you very much for connecting this afternoon or this morning or this evening, depending on where you are. So thank you very much for this. And we are, well, yes, first of all, give me just 2 minutes to start talking about what is EPIC and what EPIC is doing. Trying to put my... Okay, so yes, EPIC is the European Photonic Industry Consortium. We are around 700 companies working in the field of photonics. We have all kind of companies working in all kind of levels of the supply chain. We have companies developing software, other companies that are system integrators and users companies, and also working in all the different markets, optical communications, but also laser manufacturing, environmental, and all kind medical, all kind of markets. So we have a team of with 5 PhDs. We have Carlos Lee, our general director. We have Jose Pozo, our CTO, and then we have a marketing team. Yes, everyone working for the European photonic industry. And also, well, what we do is to organize online technology meetings. In this case, you can see here our list of online technology meetings since the beginning of this year. Now we are ready for the season 4 of these online technology meetings, and you can see here next week we are going to have challenges for laser optics, also meetings about cosmetic and beauty, meetings about optical communications such as the 400G Ethernet optics, meetings about urology, laser micromachining. And yes, at the end of this meeting, we are going to have the opportunity of continue the discussion. So please, if you want, you can connect with Wonder Me for the ones that are in the Zoom room, and we can continue the discussion. So it's time to start. Now I would like to introduce you with Tracy Bannick, that is the head of Photonics and Market Research, who is going to talk about the hot topic, this 5G, and which are the opportunities for photonics. So Tracy, if you are ready, we are also ready, and you can start sharing your screen.
Wonderful. Okay, thank you so much, Anna, and thank you all for joining us. Let me start sharing the screen here. Give me a second. And let me see here. Hold on. Just go this way. There we go. Can you see my screen now?
Yes.
Yes. Okay, wonderful. Well, thank you all for being here. Good morning, good evening, whatever it happens to be for you. We're going to be discussing 5G requirements that are going to drive photonic opportunities. The topics that we'll cover are varied. We'll start very lightly. We'll start with the long-term drivers for 5G, and these are the applications. But then we have some more immediate requirements that will require 5G upgrades within base station and front haul, and we'll be discussing a little bit of the technology associated with these areas that traditionally are semiconductor, because we need to understand what the semiconductor solutions are to be able to see how we can integrate photonic components into those solutions. So we've got a full day, and with that, let's start with the market trends and applications. Okay, for 5G, what is driving 5G right now? It's mobile communications for voice and video. So it's the being able to support the phones and the cellular systems that are there. This is the main thing that is driving upgrades for the network at this point, mostly within the metro centers. But there are additional applications that are on the way. We have autonomous vehicles, which, as you'll see in just a bit, will add substantial traffic to the 5G network. This includes vehicle sensors and control, and will become even worse as we begin to integrate artificial intelligence and processing to analyze different information coming from each individual vehicle. We have private 5G networks that are being built out now. This is a great way for larger companies to be able to build out a network on their campus or across multiple campuses without having to run cables. So this is a great way for companies to provide a more connected business. You'll also see 5G hit manufacturing, especially with industrial IoT 4.0. And we'll take a look at some of the timing considerations required for this. And then, we talked about autonomous vehicles, but there's also other transportation, such as shipping and ports. And combined with that, this will complement warehouse management, because we're going to start to see a very tightly integrated infrastructure of how goods to countries, how they are then unloaded and transported across across countries into cities for distribution. So 5G traffic drivers right now it's video. Video streaming contributes to 66% of all current mobile traffic. And it's going to get worse because there is a huge uptick in virtual and augmented reality and gaming. So this is going to help fuel additional long-term growth for cellular systems. But then we'll also see autonomous vehicles eventually will start to contribute significantly to the 5G traffic, and private campus networks as well as they expand. We've already mentioned warehouse management and the integration into industrial control systems. One mention though, you'll hear a lot about IoT messaging. IoT messaging sounds like it's going to be just huge, but you need to take a step back and look at the message size. The message size for most IoT messages is only about 2K. So these are very, very small messages for the most part. So even though there may be a lot of them, they're tiny. Now, there's one exception, and that's security cameras and videos. So when you look at videos, will they be classified as phone communications because you might receive a video security feed on your phone, or will it be classified as an IoT traffic? Basically, anything that involves video is a larger message. But there will be autonomous vehicles, small messages as well. These will come from lane markers, from roadside sensors, and also from smart signage. But the majority of communication for autonomous vehicles will be via the 5G network, not IoT sensors. Industrial control system, industrial IoT, these are small but very time-sensitive messages. They might be information about the status of the equipment, if there's a leak, if there's an error. These are small messages, but very, very time-sensitive and important. And along with those, for manufacturing, there's a potential mixture of message sizes and time sensitivity. For example, you might have on a line, what is the position of this manufacturing step on the line? Are we ready to move? But if you're looking for quality, like for example, if you're doing any laser cutting, you will probably want to see the image from what is being cut. So anything that includes images, although it might be an IoT message, remember that images are going to bump up the size of that message. But for the rest of them, they're very, very small messages that will take so very many to have any impact on the 5G traffic. Now, this is nothing new. We're seeing growth of traffic. This hasn't changed. 5G adoption began with this dotted line here, began at Q4 2018, right before 2019. So right around Q1 2019. The peak growth also occurred the same year. That was 90% year-on-year growth. But this traffic growth has continued. It's nothing unusual. We continue to see the traffic grow. What will change is that we're going to see more of it accelerate as we deploy more applications. One thing that's interesting is that the growth in 5G has already begun to displace 4G. So 5G is this orange, 4G is represented by the green, And so what you see as of 2020, 5G was already beginning to displace 4G. So we're seeing more mobile user subscriptions that are in 5G. And this happened even during a COVID year. So looking from 2020, 2021, we're seeing large growth in 5G, and the uptake is much higher, much faster than it was for 4G. So Ericsson, which had an excellent mobility report from November 2020, Ericsson anticipates 220 million subscribers by the end of 2020, or anticipated, and that was met. Now, another indicator, an indirect indicator in this case, is how is 5G doing? Well, we're seeing more 5G devices being entering the market. So commercially available 5G devices have grown rapidly. We have over 400 devices for the first time, an increase of over 33% just the last 3 months. And this represents 64% of all announced 5G devices. So the phone uptake, the 5G device uptake is really starting to hit. And then the number of announced devices hit 628 in March, just last month. So these are not sales, these are announced devices, available devices. So it's an indirect indicator, but it does show that companies would not be introducing all of these devices if they did not believe that they would be sold and if they had not already seen the sales. So we're seeing that more and more 5G devices are hitting the market. And this information was from Global Suppliers Association, GSA, a published survey. Now, this next slide, this is from Dell'Oro. Many of you may not be familiar with Dell'Oro. They're based in the US, and this is the company that you go to if you need competitive pricing information. But because of their knowledge of pricing and sales for individual companies, they create some very accurate forecasts. And so looking at what they have from this year, 2020, what they saw for wireless, they saw 7% growth in 2020, the COVID year. This was the fastest annual growth for a decade. And the report also suggests strong growth in multiple wireless segments, including one very important for Photonics, radio area network, and the mobile core. And we're seeing, as a trickle down, we're seeing capacity upgrades as well in some areas, some regions, mostly within the metro. And as Huawei is removed from some of the markets, we're seeing an uptake in that gap is being filled by carriers, by providers such as Nokia and Ericsson. So it's good news for both Nokia and Ericsson. Okay, so that's a little bit on the applications. Now, from a carrier perspective, most carriers watch the applications and are looking for the killer app that is really going to help drive 5G. And that will be more of a long-term impact. And one of the biggest ones will be the impact from autonomous vehicle applications. And let's take a look at that. Okay, autonomous vehicles currently have vehicle-to-vehicle communication, so vehicle-to-vehicle data that's shared. We have maps that are shared. Many of us drive using our map system within the vehicle. We have vehicle status information that can come from the network. And we receive software updates depending upon the age of your vehicle. But we're on the path to fully autonomous vehicles. Right now, we are at level 2. So we can do some autonomous functions like cruise control and lane centering, but the driver must be ready to take complete control of the vehicle. Depending upon what vehicle you're in, this sometimes happens and sometimes doesn't. So I'm thinking perhaps of Tesla. There have been a number of drivers with Teslas that have not provided the complete attention to driving that perhaps they should have, but that's the fault of the driver. So we're right at this point where there's some autonomous functions that can occur, but for the most part, the driver needs to be ready to take control. We're moving towards partial autonomy, where drivers are still necessary, but they need to monitor the situation but they're not required to monitor the situation as closely as they did in previous levels. But as we enter into this partial to full autonomy, we're seeing an increase in network dependence in order to support this. You need to have not just information of the vehicle in front of you, you need to have a wider range, wider view of what is happening within the traffic system. So for example, as we're driving, we may see brake lights up ahead, and so we would automatically slow. For part of the communication system, depending upon the age of the vehicles involved, our car can automatically respond. But as we moved into partial autonomy with more connected vehicles, we'll have better information that is provided as vehicle conditions and driving conditions change. So now we have the communication between vehicles that is done for safety. And here, for safety, you need the minimum amount of latency. You need the minimum amount of delay, because you need to be able to respond quickly if the vehicle in front of you just braked really hard, or if a bus just ran a red light. So today we have vehicles that can respond faster than the driver can, because it's communicating with other vehicles using something called dedicated short-range communication. This is vehicle to vehicle and vehicle to infrastructure communication. So this DSRC provides an enhanced traffic vision. So we're able to communicate conditions approximately 300 meters around, gives us good communication with vehicles that perhaps would not be in our direct line of sight. This has been done since approximately 2016. And this communication protocol, DSRC, has minimum latency and is used in conjunction with something called advanced driver assist systems. These advanced driver assist systems have been around more widespread availability since around 2017, where the vehicle can respond faster than the driver. But this is changing. We're starting to evolve to something called vehicle to everything, or cellular vehicle to everything. We're in the prototype phase. Here we're going to be utilizing the 5G network. We will be able to sense things, including people, bicycles, roadside structures. And we're going to be doing anything that is minimum latency required, doing something called a sidelink communication, which we'll talk about next. Now, for this vehicle to anything, we're going to be using the LTE chipset. So this currently is installed in vehicles, but 5G is in design and will include multicasting. So it is anticipated that we'll have 5G communication using 5G chipsets by around 2023, end of 22, 23. So why are we changing from the DSRC, sorry, that's a typo, DSRC communication? Well, it's because LTE chipsets are much less expensive to manufacture than the chipsets that are used for DSRC. So, however, safety critical systems are not expected to use 5G or the 4G currently due to latency. And what we'll see though is we'll see something called LTE-V sidelink communication. This is available in 5G, where basically the communication will bounce off of the antenna, will not hit the radio network per se, the front haul, but instead we'll use the antenna basically as a feeder. So this is a radio sidelink capability. It has short-range direct communication mod. It provides 360 degrees non-line of sight awareness. So you'll be able to get information even for conditions that are happening in front of you or behind you that you can't see. This is lower latency communication that has been designed specifically for vehicles and will include the vehicles, the infrastructure, and pedestrians. So one of the things that, one of the sensors that we will use is LiDAR. And we have a number of sensors that are implemented in vehicles, as we'll see on the next slide. But LiDAR today is a very important sensing technology because separate from a camera systems, an imaging system, LiDAR well for both day and night. There are some caveats there. And what it can do is it can provide precise imaging of any type of object, unless that object happens to be highly reflective. And it can identify both static and moving objects, so that you can have a sense if you are accelerating to something that is in the middle of the road instead of just taking a photo of it. So it gives you good information about how close you're getting towards another object. And you can use additional units so that you can see around corners. So this is important if, say, you're turning a corner and there happens to be a pedestrian that's in the crosswalk that perhaps is outside of your range of vision. And what's really promising is we're starting to see some very good LiDAR systems that are lower cost and higher definition, and do not have the same sensitivity to high reflections, to glare, or to interference. Now, the disadvantage with LiDAR is that it does not work well in water weather. So if you have heavy rain, heavy snow, it will obscure the information. The other disadvantage of LiDAR is that it generates a lot of data. So when we're looking at this, we have sensors that are available on these vehicles, and they're more than what we typically think of. So we think of LiDAR, and we think of cameras, and we think of some proximity sensors, but there are also other sensors that are installed so that you can use advanced driving, so that the vehicle can respond faster than you can. So there are a number of sensors that are available within these within these vehicles. But what's important here is that with autonomous vehicles, you're going to have something called sensing fusion. So here you have all of these different vehicle sensors, and there's a lot of them. And the highest priority is determining if there's anything that is immediately in your immediate proximity, if you're about to hit. Is there something too close that you could hit it? That's the initial sense. But then there's going to be something called sensor fusion, and this is going to be different with each vehicle manufacturer. How do they prioritize the information from these different sensors? So this sensor, the sensor fusion, is responsible for combining the strengths of the different sensor elements. So these are algorithms, and this will be company specific in most cases. And it's going to take into consideration your location that has been provided via a map, and also the communication to the other vehicles. So what's happening around you? So what's happening within your vehicle, what's happening from other vehicles. And this sensor fusion will be used to make a decision if there is an advanced driver assist system. Do we need to brake? Do we need to accelerate? What do we need? Do we need to steer? Do we need to avoid something? What do we need? What action does this vehicle need to take now? And we'll take control of that. So here we're looking at this vehicle fusion system, but we're looking at it as basically happening within the vehicle itself. However, there's going to be communication to other vehicles as well. So right now, a lot of communication is handled by 4G, such as with the GPS, but cameras and radar sensors, LiDAR, ultrasonic sensors, etc. But with 5G, we'll be able to take this full range of vehicle sensor data, and we'll be able to both monitor what's happening within the vehicle proximity process, as well as send it to the 5G network for processing. We'll have location information that currently is 4G. This is moving to 5G. Oops. We'll have vehicle communication, DSRC, which includes right now 4G LTE and 5G. And we have autonomous vehicle software updates, which currently happen at home with your home Wi-Fi network, but we'll be using the 5G network, as well as entertainment systems that will be moving to 5G. Okay, so the 5G instructions, we're going to be looking at a wider view than just the CV2X. So we're going to be taking all of this information that has been obtained from the individual vehicles, and we're going to be merging it with the information that is coming from other vehicles that are further away than what is supported with DSRC, and also with information coming from smart cities, so that now autonomous vehicles will be able to moderate their speed so as a means to avoid traffic. So especially in city centers, it's better to have things slow down rather than stop. So smart cities will be able to help control vehicle speed in order to avoid congestion. So all of this would be communicated back in through the external vehicle information, the sensor fusion, and then to the vehicle action center, which would, in this case, deaccelerate. So we're starting to see a lot more communication that will occur with 5G as a means of helping to control vehicles and traffic. For the smart infrastructure, here we see an integrated 5G support infrastructure where you can receive information on dynamic control, other autonomous vehicles like trucks, if there's any ambulances or police-assisted communications that need to occur. Not only can 5G support separate communication bands for ambulance and police, and I say bands, that's an RF application, but they can support separate information provided to ambulance and police, but there's also street signal control. And there are developing safety applications as well. Now, the concern though for using this with 5G is that there's a longer latency. So the short communication between vehicles will still be utilized. So 5G will complement what is already available within the vehicle. But it does have a potential data impact on the 5G network. So looking at all of the different sensors, whether it's a camera or sonar or radar or LiDAR, all of these sensors contribute data. And in fact, when you're looking at an autonomous vehicle, you're looking at approximately 4 terabytes of data every single day from every vehicle. And so this amount of data may need to be stored. For example, on an autonomous vehicle, let's say that the vehicle suddenly in the middle of traffic spins 360 degrees. You're going to want to determine what caused that and analyze your software. So you're going to want to store and recover, have the ability to recover some of this data. Additionally, as we begin to use artificial intelligence as a means of making faster and better decisions, artificial intelligence will also increase the volume of the information that is transmitted and stored. So this will have significant impacts on the 5G network. And when we talk about autonomous vehicles, we've been focusing mostly on cars, but autonomous vehicles can also apply for applications including trucks and shipping. So you'll see sensors that are used to improve parking and docking, especially for large trucks and for ships. And we'll start to see an integration whereby we will have autonomous ships and we will have information about when those ships are being docked and the amount of and type of information that is being carried with inventory management integration, so that now you can have very, very fine-grained control over how goods are distributed. So now this will be something that is automated, and we will be able to pack onto the correct vehicle and set it in truck convoys for inventory distribution. This will be an incredible application for 5G. And crewless shipping is going to be enabled by good position navigation and timing and 5G communication. So we're going to start to take a look at when is this going to hit. So right now, the forecast for 2021 was for 39 million autonomous vehicles. There was no separation here of cars versus trucks. However, this will probably be depressed because we're facing an incredible semiconductor shortage right now. But still, this is a large number of vehicles, but this is worldwide. So if you take into consideration the amount of data that can be generated from each autonomous vehicle, 39 million, and multiply that out by 4 terabytes per day, you start to get some pretty large network data that will be generated by autonomous vehicles. So we're going to see a ripple effect that occurs. We'll see increased carry capacity that will be required for 5G, but we will also see increased data center edge requirements to be able to receive this information. And for that, we're going to need high-speed photonic transceivers, PICs, and optical fabrics at the edge and at the core. This is a lot of information to move. And then complementing that is, as you increase the amount that is being sent to the data storage centers, that data is also going to need to be stored. So if you look at just a annual storage, you'll start to see some incredible numbers in the zettabyte region. And again, this has a ripple effect where we're going to see increased data center storage capacity requirements. All will involve high-speed photonic components. But what's even more scary is that if we look at cumulative storage of this data at data centers, that you want to be able to, maybe the insurance companies want to be able to store vehicle information and be able to reference it should there be an accident, or that the vehicle manufacturers want to be able to store information and access that information depending if there was a software glitch and they're trying to analyze what the impact of that glitch was. You're going to see more storage that needs to be held for autonomous vehicle data. So it's not just the short-term storage of data, it's going to be a long-term storage of data as well. And then you have to be able to retrieve this information as well. Will this impact the 5G network per se? No, but this will impact data centers. And as a result, we're going to see continued incremental growth for autonomous vehicle sensors. This is cumulative. This is not separated out by different sensors, but we will see autonomous vehicle sensors continue to grow, especially since most of these sensors today are being used for vehicles as opposed to trucking systems and shipping. So carriers talk about the killer app. Well, certainly autonomous vehicle traffic is going to arguably the first killer app for 5G, but it's not happening immediately. So if we look at this, the support for autonomous vehicles and the need for that support and the additional increase for 5G network to carry that, it's not going to be that great this year, even into next year. But as we start to move into a higher level of autonomous vehicle where there is less human interaction required, now we're going to start to see more and more vehicles on the road with more and more traffic, more and more data that needs to be. And so this is going to hit probably around the end of 2022, the end of next year, or around 2023, and then it's going to take off. We'll see autonomous vehicles and trucking adding greatly, as well as inventory management begins to be integrated. So this is not a driving application today. Instead, we have other conditions today that will utilize, have the opportunity to utilize photonic components. That's a little bit of backup. And so right now we're about to start on 5G station requirements. Are there any questions before we go on? Anna?
Yes, Tracy, I have a question. So then during your investigation, in order to elaborate this market report, do you think that automotive applications are going to be the main driver for Ethernet to go beyond 400G?
I think they very well could be. Certainly for 400 gig and the requirements for the data centers, you have an increased reliance upon cloud networks and cloud storage networks coming from a wide range of corporations and businesses. However, 5G for autonomous vehicles is definitely going to add to that trend. So we see 400 gig in data centers increasing, the need for 400 gig transceivers, we're going to need more. So this is going to be not just the application that fuels the data centers, or let me take that back. Cloud communication is not the only application that will fuel data centers, but also increasingly autonomous vehicle communication.
What about, I have another question. What about automation, building and industrial applications? Do you think this is also something, because you focused here on automotive applications, but what about industrial applications?
I think that for some industrial applications, there will definitely be a use for 5G. But there's a caveat with that. When you look at anything that is a chemical manufacturing, for example, oil and gas or pharmaceutical production, anything with chemical manufacturing must by necessity involve multiple layers of security and control, not just to protect the end good, the chemical or process, but also to be able to protect the equipment. So there are billions of dollars that are invested to create, say, an oil processing plant. They need to protect that equipment. They need to protect their product so that it doesn't get, so that no one hacks their system and spoils the MIPS so that they can't sell it. So for 5G, for those type of applications, I would say, no, not quite yet, because I'd be concerned about the security. But when you're looking at manufacturing for a manufacturing line, absolutely. 5G with IoT sensors, this will be a very important application.
And now, please, Tracy, take advantage 2 minutes to drink water or whatever. And now, if I am able to share my screen, screen one, just share, yes. And now I would like to show you this slide, if I can adjust to the side.
I haven't seen this one.
Yes, this is for the, well, this is our good friends from the Ethernet Alliance, and this is the 2020 Ethernet roadmap. Here, what I wanted to show you is how they have identified automotive and automation, no, regarding building and industrial, as one of the drivers for going beyond 400G. So yes, this is something that I wanted to show you. They think this is going to be the next driver, so I am happy that you got the same conclusion.
I'm glad I did as well.
Okay, then if you want, I can stop sharing my screen. If there are no more questions among the audience, and you want, you can continue, please.
Okay, so do I need to share again, or I think so?
Yes, please share again.
Okay. Okay, can you see my screen?
Yes, yes, we can see.
Okay, good. Okay, let's continue with 5G base station requirements. Now, this is the beginning of what is going to drive photonic integration into 5G now. And you need to understand that for most cellular communication, we're talking about RF, we're talking about radio frequency. This is analog and this is semiconductor components that have traditionally been used to communicate out to cell phones and to communicate to the antenna systems. So we're entering an area where we need to know a little bit about these components and the semiconductors in order to see how photonics can complement and improve those solutions. Uh-oh, I seem to be locked. There we go, okay. Now, so for 5G, we're running at higher frequencies. So we see that 5G can support higher frequencies and higher data rates. We'll see this more in a bit. And as a result, we're going to see that there's a need for more stringent timing requirements. This is essential when we are sharing the same infrastructure. And we need to make sure that we have good synchronization so that we can do handoffs. So that if you're walking, you can be handed off from one cell tower to the other, especially if you're driving, so that you can have a nice clean handoff. And so let's take a look though at the difference with LTE service the old way, and then we'll look at what's happening now. Again, this is semiconductor, this is radio frequency, this is RF. And for traditional LTE, the antenna broadcasts in all directions the same. So it's known as an isotropic antenna broadcast. And so how does it broadcast this? Well, you have a giant power amplifier that is going to be driven very hard in order to send out the radio frequencies out from this antenna system. This power amplifier is connected to the antenna system via a coax cable. So a power amplifier is analog, but there is some process, some part of this that is going to be digital. So let's take a look over here. Power amplifier, they are inherently non-linear. They do not respond respond, you would like them gone. And so you have to provide correction. So the way that you provide that correction is using a pre-distortion amp, or what's known as a digital pre-distortion amplifier that is receiving continuous feedback from the amplifier so that it can make live real-time corrections for how that power amplifier is responding. Now, this power amplifier, 100 to 300 watts, it's nonlinear. It's separated from the base, from the antenna, because it sits at the base of the structure. You have to compensate for the cable loss going up antenna. And these power amplifiers, they run very hot. They are driving hard. And so therefore there must be cooling that's provided to them, because for semiconductors, for most components, a stable temperature allows them to have a longer life. And the higher the temperature, the shorter their life. So there's going to be cooling. Sometimes you can just get away with fans, but typically it's air conditioning. And then you have the energy, the power that is going to be utilized by the pre-distortion amplifier as well. And you have A to Ds, because you're going to be taking this digital pre-distortion amplifier is going to be, we're going to be converting it from digital to analog for the power amplifier. We're going to then be receiving the feedback in analog form from the power amplifier, converting that to digital and providing the feedback for the DPD so it can fit the power amplifier. So these things, they're running hot. Now, the other thing is that because this is an analog signal, and we're looking at RF, it's an analog waveform, this waveform must be sampled at least 2 times the frequency, preferably more. And this is something known as the Nyquist limit. Have you ever seen ads that have shown a vehicle driving down a road and it looks like the wheels are going in reverse? That's because they didn't sample at least 2 times the frequency. So to accurately represent that frequency, you must sample at least 2 times the frequency. And we need to remember this because it's important for 5G. And the frequency for LTE is below 3.7 gigs for EU. Okay. So we mentioned that the base stations run hot. This is a huge business providing base station cooling systems. And we need to make sure that they're maintained at a steady temperature. You can have large rooms, you can have small little shelters, you can have a number of systems that are used, but this is a big business. Now, let's take a look at 5G service. 5G start to change. 5G, we're using antennas that are now going to be steered. They're going to be pointed to an individual cell phone user. We're using something called multiple input, multiple output, and also massive multiple input, multiple output. With these systems, instead of having one single power amplifier, we have a number of smaller power amplifiers. And we need to understand that for 5G, we're running at much higher frequencies than we did for 4G. So we have higher frequencies, and especially if we're doing any millimeter wave transmission, those are even higher frequencies. This is going to dramatically impact the sampling and the clock rate that has to occur with our A to D converters. So as we go into higher bandwidth, we're seeing increased bandwidth. We have an increased requirement for sampling and clock rate. So now these A to Ds and D to As, these start being driven even faster. They're clocked much, much faster than they were for 4G, because the signal is running at a much higher frequency rate. And as a result, the DPD, the pre-dispersion amplifier, is also running much faster and is doing far more processing. So this is running hotter and faster. And in addition to this, we have the beamforming elements so that we can steer individual beams and track individual users. Beamforming takes processing. And so although we have smaller power amplifiers, we're using more of them. And so the semiconductor company might say, oh, but these power amplifiers are using less power. Yes, individually, they're using less power. However, in an aggregate, you have more of them. So you're actually running much, much harder than you did before. So things have changed within 5G. It's actually gotten far more complex and more difficult than it was with 4G. And yet, for many of the maintain these, there are RF engineers, they've been doing this for a long time, and they don't realize the implication of what moving to 5G means, how this will impact their systems and the operation. So we mentioned that we have to start sampling much faster. We have higher frequencies. That means that we have to have faster A to D sampling. We have to have faster processing for our predispersion amplifier. That means that timing and synchronization for 5G is absolutely critical, moving to these larger antennas. We're going to talk more about this later. Now, with massive multiple output antennas, this is an array of antennas. So as you saw a number of different little power amplifiers. They're closer to the antenna, driving these little discrete chips that are make up this large antenna infrastructure. And what MIMO is able to do is it's able to do spectral reuse, and we'll talk about this more later, as a means of distributing the frequency for these devices and providing a more efficient utilization of the spectrum. And so the initial MIMO, multiple input, multiple output antennas, were 4x4 up to 16x16, but now they're much larger. We're seeing larger antenna arrays, which has increased the cell throughput. The more antennas that you use to form a beam, the narrower that beam will be and the more focused it will be. And so we're using beamforming to dynamically focus and track each cellular device. And this way, the carriers are able to provide good communication to a cellular phone, not just when it's at the base of the antenna, but also when it's at the far distance of the antenna coverage. We'll be talking much more about beamforming in a little bit. Now, what are the advantages and the disadvantages? The advantages is that there's a flexibility of coverage. You're not just generating wave RF in all directions, you're focusing that beam and you're steering it. And this gives you the ability to have increased channel capacity, which means that you can support an increased number of users. But there's a trade-off. You have to have increased power to reduce the signal to noise ratio. That's a definite trade-off. And if you use higher frequencies and reduce the antenna size, well, higher frequencies come with a loss, and you also have to drive them harder. Higher densities, higher antenna areas, well, you can be driving these little antennas that are in close proximity to one another so hard that now thermal management becomes a significant concern. And with the higher number of involved RF components for beam steering, you have a higher demand for processing. Higher demand for bandwidth requires increasing the transmit power for improved signal to noise ratio. So we're in kind of a vicious cycle. We need to have this increased frequencies, we need to have beam steering, and yet as a result, we're going to be driving the power amplifiers even harder. So 5 to 10 watts per power amplifier for sub 6G massive MIMO applications. You start adding all of the individual amplifiers. These antenna systems are running very, very hot. Now, additional advantages and disadvantages. So with massive MIMO, we can have more elements used to steer the beam. That gives us a very, very narrow beam. So we can have good focus of the beam at the end user, even if he's at the edge of the cell. And with massive MIMO and 5G millimeter wave uses even higher frequencies. And with higher frequencies comes signal loss. So the higher the frequency, the higher the loss. But massive MIMO, by using multiple elements, can boost the signal power to help improve millimeter wave transmissions distances. So what are the opportunities for photonics in MIMO and massive MIMO? We'll see more about this later. We can't change the requirement for RF power amplifiers. We still need the power amplifiers to transmit the radio frequency signals. Not until we can transmit via laser directly to a cell phone, but there are safety issues there, so we're not there yet. So we still have to work with power amplifiers, and because the power amplifiers are not linear, we still have to work with the digital predistortion amplifiers. However, we can help lower the power utilization and have a smaller footprint by doing optical beamforming. So here we're looking at the potential for a hybrid solution that leverages optical beamforming that has a combination of both RF components as well as optical beamforming components. And by handling the processing, the calculations that are needed in order to do precise beam steering, having that done with optical components, this will substantially reduce the amount of power that is required for the whole system. Two, there are some really interesting developments with gallium nitride on silicon carbide amplifiers that have a very high frequency response that look very promising, that were announced last year. Okay, so that's the introduction to what we're faced with, the antenna communication going out to cell phone communication users. But as we mentioned, we have timing considerations that are necessary with 5G networks. Anna, if there's no questions at this point, I'm going to keep going. How are we doing?
Well, Tracy, in fact, we have a question in the YouTube channel for the first part of the, regarding automotive, okay?
Okay.
Yes, the question is from Yoshiaki-san.
Hello, Yoshiaki-san. Yeah.
Yes, and the question is if there is any difference of data load, of the amount of data between pulsed LiDAR and FMCW LiDAR.
That's a really good question. And specifically given the FMCW LiDAR that's recently introduced, I will have to check that out. I will have to check with one of our manufacturers and see what the difference in the data is. Could be that there's more, could be that there isn't, but that is an excellent question. Thank you so much, Yoshiaki-san.
Okay, and we have another question in the YouTube chat. This is from Alain Delphi from Soitec. Thank you, Alain, for the question. What is the typical optical link needed for MIMO? 25, 100 gigabytes?
I'm sorry, say, what's the first part? What is the typical
optical link needed for MIMO?
So that depends upon which
that it can provide.
Yeah, it depends upon which MIMO antenna you're using. So depending upon how much spectrum you're going to support, the larger the MIMO, the more antenna components that are part of that MIMO, the larger the communication cable that may be needed. And we'll be talking a little bit more about this in just a little bit. Okay, that was a good question.
Okay, thank you. So you can continue. Thank you, Tracy.
Okay, good. Thank you. And I'll get back to both of you guys. Please, Anna. Yeah, okay, thank you so much. Okay, let me share the screen again. Okay, so we mentioned that 5G is a higher frequency signal. And as a result, there are considerations 5G. So that kind of follows, you would intuitively assume that there would be tighter network timing, but there's actually more to it than just the higher frequencies. Oh, here I'm stuck again. There we go. Okay. So the way that we used to time 3G, 4G networks was based upon GNSS. And GNSS is a foundational element in many applications. However, it's susceptible to jamming. It's susceptible to spoofing. There are systems that are being sold today that will allow you to spoof GNSS signal. And satellites too, as we start seeing more and more satellites put into orbit, we're looking at potential damage or even potential intentional destruction occurring with these GNSS satellites because they're so critical for so many applications, including for 5G. Now, traditionally with 3G, 4G, you would have a GNSS receiver for each antenna, for each base station. Costly. And they can also be subject to damage, and they suffer from some limitations in that you need to have good, clear line of sight to the satellite base to be able to receive the timing. And they can be obstructed also by weather conditions. But for this high bandwidth operation, 5G requires extremely accurate clocks and synchronization. Okay, so we talked about you can lose a GNSS signal because of line of sight. This can occur with whether you have a city like New York City, where you have many, many high rises, or in Tokyo, Japan. But it can also happen if you are trying to provide 5G coverage within a coliseum, a covered coliseum, or within tunnels or with subways, where you do not have a direct line of sight reception for the satellite timing. And this timing is important. It's important for frequency synchronization. This is the foundation for efficient spectrum utilization. And you're familiar with spectrum is a very rare, something that the carriers buy. They want to be sure that they can get as many users using that spectrum as possible because they only have so much. And the frequency synchronization is also required for base station handover. So if you happen to be going between base stations, you need to have a good synchronization so that you don't drop the call, drop the signal. So time synchronization complements frequency synchronization in many of the same ways. You need this for effective spectrum utilization as well, but it's also required when you're looking at joint processing for several base stations that are used to communicate with the same user who may be at the border of a particular cell. And it's also used to correct, to provide time synchronization for different radio frames that arrive at different times because they're further away, because they are at a different distance. So you need to be able to correct those radio frames. You need to be able to synchronize them. And synchronization is also important for roaming. So with roaming, especially when we look at vehicles, the networks must be able to sync for seamless handoffs for autonomous vehicles. So this becomes increasingly important as the autonomous vehicle communications expand to include more traffic and safety information. We must be able to provide continuity. And two, timing is very important for industrial 5G applications. We must have accurate synchronization, accurate orchestration of the entire assembly line for the entire process. And this requires 5G and time-sensitive networks. So what other systems require this level of accuracy? What other systems acquire their time GNSS, their timing base? Well, anything that is involved with navigation, position, and control, such as aeronautics and shipping, industrial control manufacturing systems, as we've just seen, quantum applications, space operations, certainly, and 5G telecommunication systems. So at this point, everything's moving so fast. We have to be in sync. 5G networks support higher frequencies and higher data rates. And so therefore there are more stringent timing requirements, and there needs to be a common time base for all communication devices. Everything must be in sync. This becomes increasingly important as you have a number of users sharing a common time source. Now, what has happened with 5G is that there are now new enhanced accuracies. So for example, you used to have accuracy requirements, absolute timing error requirements in the millisecond range. For 5G Class C, we are now in the 30 nanosecond range. We're looking at a difference between a millisecond and a nanosecond. They are much, much tighter requirements for timing. And there is even a Class D requirement for 5 nanoseconds. So we need bandwidth aggregation that requires precise clocking with nanosecond accuracy. So we could equip each base station with a GNSS receiver. However, that will get a little bit expensive, and we'll talk about this in a minute. But for right now, there's another difference between 4G and 5G, and it has to do with the Common Public Radio Interface, CPRI. Okay, so CPRI was what was used for 3G, 4G. CPRI defined the interface between the radio equipment and the radio equipment control, and it was based on time division multiplexing. So there was time included in that signal, and there were variants with this. So this tended to be very proprietary, and there would be individual manufacturer variants, which meant that you were locked into an individual provider. Now with eCPRI, which came around in 2018, this is the evolved Common Public Radio Interface, and it's also referred to as the Ethernet Common Public Radio Interface. It is based on Ethernet. The goal of eCPRI was to provide more flexible and a cost-efficient front haul with better efficiency, not just with cost. And it supports speeds of 10 gig and higher. But eCPRI requires a timing synchronization reference. It's Ethernet based. You have to give it a synchronization reference. And this is so that it can accommodate delay and jitter, correct for that. But the key thing is that it does not maintain the synchronization. You can't give it to it once and expect it to continue on its own accurately. It needs to have a continuous, accurate synchronization input. And eCPRI, the advantages here is that it's vendor agnostic. This is a good thing as we move towards open standards. And it's more efficient. With eCPRI, you can have a 10 times reduction in the amount of required bandwidth because eCPRI is not a chatty protocol. So we can take that bandwidth and we can use it for direct applications instead of just using that for timing. So it's a very precise, efficient protocol. And it's standards based. So it's no longer something that's proprietary based upon the manufacturer. So how do we do it? Do we put a GNSS system on every base station? Well, 5G is going to need more base stations. So the approximate coverage radius for 5G is around 100 to 300 meters. This is much lower than what 4G could accommodate, where in a flat suburban area, you could have base stations that were 2 and 3 kilometers apart as opposed to meters. So we're going to see an increased number of base stations compared to the number of 4G base stations. So we're now looking at more base stations, more antennas. And as an estimate, if you look at, there was approximately 3.72 million 4G base stations in China in 2018. If they upgrade all of those to 5G, they're going to need more. They're going to need approximately 7.5 million base stations. That's a lot of GNSS receivers. Now, what's the economic feasibility of installing a GNSS receiver at every base station? I looked at just pricing off of Google, and I found ranges from $3,000 to $30,000 each. So I don't know what the average price is, but it's not cheap. So it doesn't make sense to install GNSS receivers at every base station if there's a way that we can work around it. And there is. We can do something known as an optical timing network. And the way that this will work is that we'll take and we'll eliminate the need of GNSS devices at each base station. And we will move to a centralized GNSS-based timing network. So utilizing this centralized optical timing, we can replace the GNSS systems. We can use cesium clocks. We can correct them for UTC time. We can provide high accuracy distribution of that clocking information using a standard IEEE 1588HA for high accuracy. This is also known as White Rabbit, which sounds kind of something that you wouldn't want to rely upon, but you really do. So we'll talk more about White Rabbit in a minute. And then this is going to be further communicated out to the base stations by using something called precision time protocol. And this is not point-to-point protocol in this case, it's precision time protocol, full timing support. This is enabled by using something called LSTAB, which is electrically stabilized optical fiber, very high performance fiber. And typically you assume that fiber is a symmetrical link where phase and fluctuations, any delay is similar for forward and backward directions, but that's not always the case. And so what White Rabbit can do is it can correct for fiber asymmetry. So White Rabbit, that sounds like it's a cartoon character, was actually something that was developed for CERN. So it was developed to renovate CERN's timing system. It can support sub-nanosecond accuracy and picosecond precision of synchronization. It's standards-based. It extends the precision time protocol, and it's incorporated into the newest revision of IEEE 1588. And it can support distances of 10 kilometers or 100 kilometers between network elements. So you can have a centralized timing network that can be distributed across the entire country. And what White Rabbit offers is better accuracy and reliability compared to GNSS. It's very accurate. It supports even class C of the absolute time error requirements. We have sub-nanoseconds network synchronization. It is 6,000 times more accurate than GNSS GPS. And it integrates with standard solutions, precise synchronization source for not only 5G networks, but also any existing 4G networks as well. And it's distributed using existing optical networks. And the reason for this, so it's not just the cost to eliminate GNSS systems on each base station, but it's also the vulnerability. So as we have more and more satellites that are being launched out into space, we're seeing a lot of debris that is accumulating. So there can be accidental collisions, not just of big particles, but really damaging collisions with very, very small 1 centimeter particles that can damage or jeopardize the GNSS system. Now, certainly there's backup, but the chances of this happening are increasing in frequency because of the amount of satellites that are in space and debris. So within here, you'll see the low LEO, the low Earth orbit. We have a very high concentration of objects that are available there, but it's actually distributed across the LEO to the MEO to the GEO Earth orbit systems. And so there's even so much of this that there's a subscription service that you can pay for to track all this stuff. So it's definitely a consideration going forward. So by providing centralized timing network with White Rabbit, you're able to no longer require GNSS receivers at each networks, at each base station. You're providing very accurate time and synchronization, which is absolutely needed for 5G networks. And two, if GNSS were to be lost, there's a UTC offset that can be provided. As long as you've connected once to a GNSS satellite, you can save that offset and you can apply it even should that the GNSS system be lost. So this provides a great way of being able to substitute multiple GNSS devices with a single network. But it's more important than just that, because not only do you have to have this timing network available, you have to distribute it, you have to share it. And so you have to be able to share it with your base station and also with your front haul. And here you see eCPRI. So eCPRI is going to be used to help share this timing, this frequency. And it also works together with something called IEEE 802.1 CMDE, which allows for something called time-sensitive networks. Anything that is hardwired. So here we've been looking at RF, we're looking at radio waves, but now back here we're looking at hardwired signals. So this includes the core of the network, including switches and routers, but it also includes the new front haul that is being developed that is part of Ethernet. So we need to be able to distribute this highly accurate and synchronization, especially to the station, but the IT equipment must be able to support it as well. In order to do that, there's a different protocol. They use something called time-sensitive networks. And this helps ensure that the network and front haul equipment is synchronized using appropriate protocols, the most current protocols. So accurate synchronization means that you're going to have efficient spectrum utilization to deliver high bandwidth, high speed services, and support of time-sensitive applications. Now, there's one caveat here. These time-sensitive networks, we require those devices to be able to do time-sensitive network timing. The existing networks can't do that. The existing switch and router equipment that is currently installed worldwide cannot handle time-sensitive networks. This all needs to be not upgraded. It can't be upgraded. It must be replaced. So we'll see how that will impact photonics going forward. Now, looking at synchronization throughout the network, the thing that becomes the common base, the common mode, is this IEEE 802.1 CMDE, because it's used not only for wired networks, switches and routers, but it's also used at that demarcation point between the front haul and the radio waves. So as we see here, time-sensitive networks are being used within switch and routers, but it's also being used for the front haul equipment, which we'll talk about more later. But the distribution of the frequency is going to be this, this base station is going to be directly timed off of the centralized core timing. And the centralized core timing will also be timing the time-sensitive networks. So there's two different modes of implementing the time. For time-sensitive networks, it's a bit more indirect. So now with this solution, we can have accurate synchronization, which means that we can make really efficient use of that very special spectrum that the carriers have paid so much for, so that we can deliver high bandwidth, high speed services, and we can support time-sensitive applications too. And the impact for the photonic industry is that we need ultra-fast lasers, we need higher speed transceivers, we need higher frequency components, and we need upgraded optical networks. Couple that with the complete replacement of existing switch and router equipment that supports 4 and 5G networks. We're looking at increasing the fiber networks, increasing the interfaces into larger capacity switch and routers, and even using an optical-based switching core. So there's an incredible opportunity now. We don't have to wait for new applications. This needs to be done now. And the carriers are well aware of it. However, it's been pretty quiet because this is not something that you want to tell a consumer who's about to buy a 5G phone, but they recognize that this is a problem that needs to be solved. So as we mentioned, these switches and routers cannot be upgraded, they must be replaced. And one more thing that's going to be influencing this and is actually going to help reduce the cost is that additional time-sensitive network replacement can use something that is software-defined networks, open software-defined networks, so that you're no longer going to be restricted to a single manufacturer, a single vendor. You no longer have to have Cisco through your network, or Juniper or Ericsson through your network. Now you can buy the best solution for your particular network, your particular applications. And all of the European carriers are all on board on this. They've been doing extensive testing. And what this does is it allows them to reduce the cost of new systems. It prevents them from being locked in and with a price for individual manufacturers. And it also allows them to be able to select the best of breed systems and take advantage of some of the newest developments that are hitting this network. That includes the latest in optical developments. So now carriers will be far more open to try new things depending upon what their requirements are for their particular area. And there are other synchronization options that are emerging coming out of blue space. ADVA was able to do a highly accurate latency measurement system that uses continuous monitoring of fiber latency with accuracy orders of 2 to 3 orders of magnitude better than some of the current systems that are already installed that are not working at this level. And optical systems will support, just naturally, both timing and capacity. So we're going to see the highest capacity per fiber with the lowest latency. And as we start to see connections to those antennas, we're going to see that part of a fiber network. And that brings us up to front haul with open radio area networks and open software defined networks, and it's 7 hours. Okay, any questions, Anna?
Yes, we have, I think we can have a comment from Amir Gadimi from CSEM.
Okay.
Hello, Amir. Maybe would you like to comment about your platform that could be ideal for 5G applications?
Yeah, sure. I mean, thank you, Anna. Can you hear me?
Yes,
Yes.
I mean,
Yeah,
yes,
so I
you
mean,
were commenting on this, and we would love to hear about this. Yes.
yeah, I mean, like as a response to your question, actually, I see a lot of opportunities for really peak to be involved in, 5G. I'm actually personally loving this, sort of presentation and learning quite a lot. But I see actually a lot of opportunities for peaks. I mean, we are developing a platform foundry at CSEM based on lithium niobate insulator. And I see a lot of actually potentials for this, not just in a traditional like digital telecom, but also RF over fibers in antennas that actually presented before. I mean, one advantage of our platform is really this, low losses. So the fact that actually we have very low power consumption at very high speeds.
Perfect.
So yeah, this is really interesting. Thank you so much for this. I mean, I'm really enjoying the presentation.
Oh, I'm so glad because we have another hour to go. Thank you so much, Amir.
Tracy, maybe I would like you to take a rest now, and we can have a small overview of what you were saying.
Okay, I'm going to turn off my camera temporarily, and I'll be right back. Thank you so much, Anna.
Yes, please. And now, okay, I'm going.
There we go. Okay.
Maybe it's a good. Okay, I guess now you can see the presentation more. So maybe it's a good moment to have just a 5 minutes, 3 minutes overview of this last part that Tracy has been explaining. So yes, well, apparently these GNSS or the GPS receivers are very fragile, and they could get damaged because of, I don't know, explosion or intentional destruction. And then what it seems is that this 5G, because of the high frequency and the sampling, it requires synchronization, right? Timing synchronization. Also, yes, this picture, I like it very much. Yes, also the GNSS receivers, they are affected by shadows, okay, in buildings. So this is a problem for this kind of devices. Also, about this, yes, so in order for communicating, autonomous vehicles needs to synchronize and needs to move and to have well distributed synchronization. Also interesting what you have been explaining about the systems, the aircrafts and ships that also are going to take a lot of bandwidth, no, from 5G to all be synchronized and well, in order to be monitored, right? So yes, I think these were the basic. A basic overview. So now there are, sorry, I'm waiting for the nice slide about the opportunities for photonics. Yes, here. So there are many opportunities for photonics. Also very interesting to know about the white rabbit that was developed first for the CERN, right? So so then, yes, very interesting opportunities for photonics that are, well, the conclusion will be about integration of ultra-fast lasers, higher frequency components, and upgraded optical networks. Okay, so this is more or less, I mean, my super modest overview. So Tracy, if you want to come back to your presentation.
Wonderful. Okay, thank you.
I need to stop sharing and you need to start sharing again.
Okay, thank you. Okay, and let me minimize this. There we go. One second.
Slide number
there we
74.
Go.
Sorry, slide number
74. Okay, here we go. Now we're going to get into the front hall, and we're going to look at open radio area networks and also software-defined networks, which we've already touched a little bit on SDN. So one of the things that's happening with 5G is that there's an evolution in the cable deployment. So we now have, we're making a move off of copper and to fiber, and also we're moving towards microwave, so that now we can actually provide communication to another end without having it be connected via fiber or via cable. So we can communicate directly between the antennas. And so these fiber connected radio sites are expected to increase significantly, but also there's going to be an increase in the number of antennas that are going to be connected one to the other by using 5G. And so when we look at this front hall, so this is the section of the network that communicates to the antenna, there was some excellent work that was done. I've been really impressed with a lot of these European projects. The Metro Hall project, it just completed. And what they did is they looked at what was going to be needed for the metro network. How would they be able to scale for 5G? How would they be able to implement an all optical system that would be cost effective, energy efficient, and software defined, would be agile, be able to be modified dynamically. So what they've looked at is they've looked at using some very short reach DWDM and very low cost, high speed fiber. And they're investigating, single mode versus multi-core fiber versus hollow core fiber. And they're looking at moving resources towards the edge of the network, so that now you say that you want a video, you no longer have to connect your phone to the, go back to the mid hall, the back hall, obtain the video from Netflix and then download it back across the entire network. Instead, you can have caching that will occur within the local network, the local edge. So they're looking at migrating a lot of that, migrating the edge network to more optical, and they're also looking at implementing more distributed networking, more caching, so that you're not required to go to the remote data centers. So they did some excellent work on this. I would strongly recommend that you check out any presentation that Andrew Lord does of BT. And there are a number of his presentations available, but this is an excellent project and it's going to continue to inform us as we move forward. But this Metro Hall will actually become more deployed as the applications increase. So this is something to keep in mind, because you want to be sure that you're positioned to take advantage of it. But now, as we are evolving from 4G to 5G, we're seeing more options for the front hall. So it used to be that you used a 4G remote radio head with a big baseband unit that was typically proprietary. And this system was very expensive. And now we're moving towards open structures, open standards, and open RAN, so that this can be, instead of aggregated, it can be disaggregated, so that we can have odd combinations of the components and functions within the antenna unit, the base station, the distributed unit, and the central unit going into the 5 core. And what will really support this is open RAN testing. This will support interoperability, and it will also support savings up to 40%, which is significant. And this also provides for architectural flexibility, so that now you'll have basic functions, but they might be kind of mixed up. So you might have some in this spots where typically they would be over in this spots. So it's the definitions of these different functions is no longer quite as clear. So you'll have the same functions, but they might be housed in a slightly different chassis. But this disaggregation, when you do this, there's an even greater requirement for timing and synchronization. So whereas the timing and synchronization used to happen within one system, now it's happening across multiple systems. Okay, we'll mention that. And what we're seeing is we're evolving from what was a traditional radio area network, a traditional RAN, into an open RAN. And carriers have been testing this, and it looks very promising. So the ORAN Association is doing extensive interoperability testing. But here you see that we're evolving from the BBU, this large baseband unit, going into individual DU, CUs until we can have DU and CUs that are going to be from different vendors. So we no longer have to stay with a single vendor. Some of the advantages of an open radio network, this is part of the front hall, that is created from diverse sources, is you have no manufacturer lock-in, which means that you don't have to pay an excessive amount for subsequent equipment because you're locked into it. You can purchase the best of the breed equipment. So if there's new innovations, you can purchase that. It can be an operator-defined solution rather than a vendor-defined solution. And the solution can be determined by where you're going to be installing it. And this will support multiple deployment architectures. If you don't need a giant BBU, you don't have to install them. You can install smaller units instead. This has the potential for reducing carrier CapEx by as much as 40%. This was reported by Rakuten. Rakuten is one of the smaller 5G networks. Larger carriers will have more negotiating power. So this is, all of these guys are online with this. Telefonica, Vodafone, Orange, Deutsche Telekom, they all support ORAN as a technology of choice. Now, there are concerns with an open system. Will you really be able to integrate it completely? And how reliable is it going to be? This is one of the reasons why they're doing extensive testing at this point. And will there be true interoperability? Certainly looks like there will. And will there be any potential difficulty in troubleshooting? At what point, where do you determine where there might be a MAC error? There are some intellectual property concerns of some of the carriers and a potential loss of security as you have different approaches from different vendors. However, if we look at what can be done, right now we're seeing that a number of the Huawei equipment systems that have been deployed, certainly within the US as well as within Europe, that as this equipment is removed and must be replaced, this open RAN is a very good solution because you can replace it at a lower cost and have more functionality specific to what your needs are. Now, there is one piece of the Open RAN policy, Coalition blocked Huawei, and they also blocked Nokia and Ericsson. But for you guys, that doesn't matter. You're good. So ORANs are an option for Huawei equipment replacement. With this was part of the security, potential security risk that was identified. ORAN is the leading candidate to eliminate Huawei 4G gear and replace it with 5G. And so this is something that is being done now. And Facebook, their Even Start program, also sees ORAN as a potential to eliminate vendor lock-in and price. So we're starting to see this shift now. So it's no longer just the big box systems that will be selling into the front hall. This opens up the environment for a lot of small different manufacturers, and the carriers will be choosing specifically what they need. So complementing ORAN is, as we mentioned before, software-defined networks. And so they are all testing this equipment at this point to make sure that there are no glitches. And guess what? There aren't. They're really happy with it. That takes care of that section on the open front hall. But now let's get back into beamforming, because there are some incredible photonic opportunities with beamforming. So this is not a presentation on how to do digital beam steering. We're not going to get into the math. I'm going to do lots of pictures, but just to give you an idea of some of the concepts that are involved. So what we want to do with a MIMO antenna, a multiple input, multiple output antenna, as we mentioned before, is we want to be able to steer and track the individual user. So let's say that we've got a user over here, this user may move. We need to be able to track that user. So the way that that's done is by using a phased array system. And there are a number of different ways that a phased array system can be implemented. But if you think about throwing a rock into a pond and watching the ripples of the waves that extend out from where the rock landed and then where they reflect back. In much of the same way, when you steer a beam, by controlling at what time the individual element fires, you can help control, you can actually help create basically a cone of how this beam is going to be steered. So if we were to try to steer something here, the element over here would have to fire first. So you'd have to be able to time it so that you can steer this beam. And the more elements that you use, the beam can be better formed, better focused, and better steered, and the more precise the beam. Now, we talked about the base station calculations that are needed in order to make the beam steerable, to make it very fine, very narrow, but also to be able to move it. So dynamic, this needs to be dynamic. And so what that can do is that if you look at massive input, massive output antennas, now we're not just looking at being able to steer the beam on the horizontal direction. Now we can steer it vertically as well, which is very interesting when you start deploying this within cities. You can actually steer the beam for elevation for people that are within a particular high tower, high building. Now, the other thing is that optical 3D beamforming is also emerging. So looking at this, there was something called Blue Space. This was another EU initiative. Is Paul van Dyck in the room by any chance? Anna? No? Okay. Well,
no.
huh? What is that?
You are asking if there are questions right now?
No, is Paul van Dyck in the room?
No, but we have
Okay.
Someone from Lyonics in the room.
Lyonics, okay. So this was part of the solution that was done for Blue Space. So in this case, the beam steering is not only to mobile users, as we had just mentioned, but now you can use beam steering to go to other locations. So basically, you can eliminate the need for trenching to another base station. So this gives you the ability to do beam steering between antennas. And you eliminate trenching, you can dynamically implement it as needed, but there's a caveat. You'll never guess what that caveat is. You have to synchronize. Time synchronization is critical, especially if you're going to be able to connect to a different carrier's equipment. Okay, moving to another little section, optical beamforming, which is also known as, excuse me, optical beamforming network, OBFN. Optical beamforming can be used for a number of different applications. So we've been talking about 5G communication, but optical beamforming can also be used for automotive, like LiDAR. It can be used for robotics, can be used for medical imaging, OCT. It can be used for avionics and also for radar and for space applications. So the advances in optical beamforming and steering offer high performance, low power utilization, and flexibility for a wide variety of different applications. And for this, high bandwidth 5G requires a very precisely steered and focused beam for both high bandwidth accuracy and high data transfer quality. And it needs to be fast, and optics can do this very quickly. So this is a basic block diagram. Really, really basic block diagram. Here we have the optical beamforming network. So basically you have the reception antenna array. You do electrical, this is RF, electrical to optical conversion into the optical beamforming network. Here's the control, where do you want to go? And then you can, again, convert it from optical to electrical for the RF signal. So just really basic beamforming block diagram. This is an example. We're not going to go over it, but I'm providing it here because it's referenced in a good journal from 2019, IEEE Photonics letters. And it talks about some of the different components that may be utilized for optical beamforming. From this would be like a laser diode, so this would be more in space, but it can be used, a wave, array of waveguides, variable optical attenuators. This is something worth taking a look at a later time. Now, another feature from the Blue Space project, and this was with FITS, this was the ability to use millimeter wave beamforming as a means of extending a network. In this case, they're using a multi-core fiber network. And this can be either analog over fiber or digital over fiber. And this was done to stress the performance of an integrated beamforming with multi-beam capabilities for this network. And it supports millimeter wave. So this is just one example of an optically steered beam that lends itself to not just terrestrial use, but also to terrestrial and satellite communications. So going back in 2018, there was a wonderful award that was given to, I'm sorry, can you please say this for me, Anna, so I don't massacre it? Institute of Telecommunications, I believe it's in Portugal.
Institute of Fraunhofer Portugal Challenge?
Yeah, it's the little gray. Yeah, so this was part of the Fraunhofer. Yeah, thank you. So, and this is applicable for both MIMO antennas on Earth, MIMO antennas in space, and also satellite communications. So here, this is photonic beamforming processes that are capable of processing many RF signals with very broad bandwidth. And they won an award for this. So their first patent was for photonic beamforming for transmitting. And then they also won a second patent for photonic beamforming phased array for receiving. And this is their block diagram. So what you see is, this is the semiconductor stage. This is the RF side. This is the RF side. And in here, this is the optical piece. So this is an example of how you can replace semiconductor beamforming with optical beamforming. And there were other studies that were done, like for Beacon. So they were looking at very high throughput satellites and on-the-ground satellite communication, including 5G, and how would they handle this high bandwidth and low latency and low power consumption. And so basing this on very widely known technologies, including WDM and hybrid beamforming, they were able to come up with a solution using optical beamforming. And you're probably already familiar. There are a number of photonics that are installed typically in satellites, and they're done so because, gee, they're smaller, they use power, they have a smaller footprint, and they're fast. So you can have all kinds of different ultra compact beamformer chips based upon multiple materials, very low power consumption, and you can have this wonderful leveraging of those two particular patents. And IMEC has created an optical beamforming device on a chip. So on this particular solution, we have silicon nitride as a waveguide and antenna, which offers low loss, high power handling, which is absolutely needed, remember, for our power amplifiers. So we need to be able to handle high power for terrestrial use, and good process control, plus silicon photonics for the phase shifters and on-chip photodetectors. So this lent itself to a very low power operation with high volumes and a reduction in production cost. So we are already starting to see optical beamforming being used not only in space, but also here for terrestrial applications. And one of the more interesting ones, not that IMEC wasn't interesting, but this is an interesting transmitter receiver. This is an antenna, and it's using optical beamforming. It's based in the UK, and it's called isotropic systems. And what you'll notice is they have different elements that can be installed for this particular antenna, depending upon how narrow you want that beam to be, and how much you need to be able to transmit, perhaps how many carriers are you supporting. So they've received some very good funding just recently and are heavily involved, as are a number of different optical beamforming solutions. So right now we're starting to get into satellite communication, and I want to make sure that we have a common base with some of the terms that are going to be floated around. First off, we'll talk about LEO, a low Earth orbit. So a low Earth orbit, in this case, satellites travel much faster than the rotation of Earth. And depending upon where they are in the orbit, typically be visible for about 9 minutes, and that's it. So this is what SpaceLink is doing. So they have that array of antennas because you can only focus on one for about 9 minutes, and then you have to go to the next. But that's low Earth orbit, so moves very, very quickly. Medium Earth orbit, this is where you have the GNSS satellites. So the orbital period for a medium Earth orbit, which is about 2,000 kilometers, is around 12 hours. So they're going to rotate, but there are a number of those that are available and can be tracked here on Earth. And then there are the geosynchronous orbit, which is the furthest orbit out that we're showing here, which is a distance about 36,000 kilometers. And with a geosynchronous orbit, it's orbiting the Earth at the same rate as the Earth's rotation, so that satellite is always in sight from the same location on Earth. This is where you typically have deployments of weather and communication satellites. So geosatellites and data. Geo, as we just mentioned, the geosatellites, the orbit is equal to the Earth's rotational period, so they appear to be motionless if you see from the ground. These satellites can cover a very wide area, so they can be useful. Say that you want to communicate to say a large data center. This could be a very good utilization. And typically, at least what they've done in the past for broadcasting, they would have an array of fixed dishes for reception. So what they were doing, there was no moving parts, but with all of those different dishes, they could also use that as an array in order to tune the beam. So the disadvantage, the drawback of geo orbits is that they're far out there, so they have a long latency period. So there was internet satellite that you may have, Hughes network. So Hughes network did offer satellite internet. However, you would take a long time to get feedback from your request, simply because those satellites were so far out in the geostationary orbit. So now we're looking at satellite internet. And what's being deployed now are satellites that are in the low Earth orbit. And so that low Earth orbit, it's much closer. You have a much shorter distance to propagate the information back to the Earth. They're only about 2,000 kilometers or so. And they offer very high quality services high quality internet services compared to what was traditionally offered with geosatellites. So they're much more responsive, they're much faster. The ground transceivers can be a dish, or it can be those new small transmitters and receivers, which gives us a lot of flexibility. And communication satellites are currently being launched within the LEO. We're seeing a lot of them launched last year, this year. They include SpaceX's Starlink satellites, OmniSpace, OneWeb's Telesat, and others. So LEO satellites are better for data. So the orbital period is much faster. You don't have as much time, so you're going to have to track those satellites to be able to receive your information. So they must be tracked. Traditionally, these were tracked with a large moving dish, but now we can track them either electronically or optically. So we can do optical beamforming to track these satellites. And the advantage is that they have lower latency, and you can put this beamforming within a very small package. This is the Kymeta antenna system. And in fact, speaking of Kymeta, they have a new U8 receiver transmitter. It's a hybrid for satellite cellular connectivity, and it's a part of a collaboration between Kepler Communications and Kymeta. Look at Kepler Nest. And they use electronic beam steering using metamaterials, and they track very fast-moving LEOs. And they can switch to other satellites whenever the constellation is out of range. For this particular transmitter receiver, they can operate in the Ku and the Ka bands, and they have a partnership with Intelsat and Cubic Telecom, which we actually heard from Cubic at one of the more recent quantum meetings. So as mentioned, Kymeta works with Kepler Communications, and Kepler Communications has deployed a nanosatellite constellation system. They were the first commercial Ku band LEO satellite called the KIP 2017. With the Ku band, here you're handling substantially higher frequencies than traditional nanosatellites. And so this allows you to send more data, so you can handle an increased bandwidth for larger data applications. So this is a big advantage for Ku band. And to do this, their satellite system consists of a sophisticated antenna array with small elements necessary for the Ku band higher frequencies. These are also in a LEO orbit, and they are reconfigured. So they are reconfigurable software-defined radio at the Ku band. So at this point, this would certainly be a candidate for optical beamforming. And SpaceLink, we've all heard of SpaceLink. So SpaceLink communications has an incredible amount of investment in it. It consists of their LEO satellites that will be communicating with Earth-based users, individual users that will have a dish. They're calling it Dishy McFlatface. So this will communicate to the dishes at the users. And these users, they only have 9 minutes to be able to see that one LEO satellite. So the dishes can switch to the next as this one disappears over the horizon. But you want to be sure that you have continuous communication. And so what SpaceLink has done is that created a relay communication satellite that is up in the MEO orbit, so that is in the mid-Earth orbit, so that it maintains communication with each of these LEO satellites to be sure that there's good continuous information. And it can also communicate directly with a receiver station down on Earth, a terrestrial-based receiver system. So this relay network system is really interesting. It uses something called always in sight because they've put up these strands, these strings of antenna arrays, of satellite arrays. We collect the data, it collects data from the LEOs, it relays it to the different mid-Earth orbit satellites, and so that we will always have good, consistent communication, even if there should be a failure. And they leverage their Starlink satellite arrays that you can see sometimes in the night sky. You can see a row of bright little stars, and that's the Starlink satellites. They utilize ultra-high frequency band, 24 gig, and they connect stationary antenna terminals down on Earth. And this is their system. You order this little dish, I think it's about $900 now, and they plan on having service available end of this year, beginning of next. So that's it on SpaceLink. Now, Omnispace. Omnispace is doing something a little bit different. They're also doing satellite to terrestrial communications, but they're going to be based on a hybrid 5G network. And so they are developing standards in order to support that 5G non-terrestrial network. This technology is powered by, they've got a lot of purchase spectrum span, and they're looking at direct to satellite communication networks using this non-terrestrial network architecture. They've developed a number of standards and communication bases in order to support this, because they're not looking at supporting just individual users. They're looking at supporting enterprise and government networks. They've demonstrated off-the-shelf availability, that it works, and they just had a big investor. Lockheed Martin has just invested quite a bit in Omnispace, and to date, they've raised $140 million. So the space satellite market is booming. There's lots of opportunity here, because for the beamforming, we can do not just semiconductor, we can do optical. But there's one more thing that is happening in space, and that's free space optics. So free space optics communications, these are laser communications. They're not so useful for communicating down on Earth because they have to get through the atmospheric layer, and there's lots of distortion that occurs at that point. So, but they're very useful for satellite to satellite communication. And as a result, so you'll see these being used for some of the inter-satellite communications, but you're also starting to see developments occur for being able to compensate for that atmospheric conditions. So there's a number of new algorithms that have been introduced. And there's also an investment, an EU investment in Tomcat product, which is looking at how to enable laser communications. You wouldn't see this, but how to enable laser communications from terrestrial to space. So some of the new atmospheric correction algorithms are basically around how to correct for atmospheric distortion, or how to basically use some type of noise cancellation, so that if they see this distortion, they apply the exact opposite of it. So it's additive, much like you have in noise canceling headphones. So they're looking at seeing if they can correct for the atmospheric layer challenge. And if so, this shows a lot of promise. And there have been a number of articles, and I'm referencing one here in the presentation, and that's with the Nature. They recently had a Nature article. So that takes care of satellite communication. Keep in mind that for satellite communication, already you're using a lot of optical beamforming, but there's still semiconductor beamforming that's being used. This is a great market to enter and be able to immediately have the advantages of photonic optical components understood by the space industry that is constantly trying to reduce the footprint and the power of their components. Now,
one question, Tracy, one question about the previous part. So then have to find examples of photonic communication between satellites and ground station, or everything is still working through RF?
It's still a mixture. So as we've seen with some of these satellites, they're still using semiconductor beamforming. But some of them have moved to optical beamforming. So this is a great time to attend some of our online technology meetings, easy for me to say, our OTMs that are involved with space and quantum, because you'll get to see a lot of the players that are operational in this space. And you can make contacts, and we can help you, and certainly Jose can help you. So yes, it's still a mix, but that's okay. That indicates that there's a great opportunity. And it's not, you won't be the first one that has to prove your solution. Okay, another question?
Well, no, not a question, just a comment. By the way, Paul is watching the event and congratulating you for the nice work in YouTube. And well, there are our companies in the room are really interested in these new opportunities in 5G. So we have Eblana Photonics in the room. They are interested by these high power lasers that are going to be needed. Also, we have connectors and transceivers for satellites. So interested also in 5G. We have foundries such as Lionics, such as Ligentech, also very interesting for these ring resonators, for beamforming. Yes. So yes, thank you very much, Tracy. You can continue.
Oh, well, I mean, I've had lots of input from different people, including Paul and others, and especially from Deutsche Telekom. Deutsche Telekom was very open in sharing a lot of information, and I really appreciate some of their development efforts on the timing network. So I meant to say that earlier. Okay, 6G. Are we ready for 6G? Well, the only reason I'm bringing it up is because it's still years away, but they're looking at having terahertz communication. So 6G would be terahertz communication, and this is at this range of the spectrum. So how can you transmit it? So you can either up convert it, or you can down convert it, or you can transmit directly using quantum cascade laser. So it remains to be seen what will be the best solution. So certainly there are electronic solutions, there are optical solutions, and then there's also quantum. So I just wanted to mention that. The other thing that looks really interesting with this is, how do you get the transmission power? They've proved that they can do amplification with carbon nanotubes. So that looks really intriguing. So this is just something to be aware of and keep your ears open to as we go forward. And then also RISE 6G. This is a 3-year EU project, that is looking at creating on-demand, dynamically programmable video surfaces, which is going to change part of how we receive information. So this looks interesting, another thing to keep an eye on. Okay, so we've had lots of good news. Now there's a little bit of bad news. So what are some of the factors that will slow the 5G new equipment build-outs? Well, one of the biggest things right now is that the semiconductor has hit a downturn. This was a result of, we were coming out of the COVID period. Manufacturers had seen fairly good growth and usage of semiconductors throughout that period, but they anticipated that there would be even more going forward. And so people started to buy, that led to a shortage that was complicated with China offering incentives to purchase electronic and autonomous vehicles, and the Taiwan semiconductor manufacturing encountering a drought, and they need water in order to manufacture semiconductors. So all of these things have kind of converge together. So now we have autonomous vehicle manufacturers that are competing for semiconductor components against the typical cell phone users, cell phone manufacturers. So there is a downturn in semiconductors, which may lead to a slowing in deployment of some equipment, because as we've seen for the front haul, power amplifiers are semiconductors. So that's going to reduce their availability. And then the other vulnerability, Jose constantly looks at and talks about who is your solution, who are your partners. Anna and the other doctors will create a solution based upon the entire stream of I'm losing the word, Anna. What do you call that chart that you make? The one that shows all of the different vendors?
You mean the supply chain?
Yes, thank you. The supply chain. That was what I missed. So you need to have a supply chain, but I would phrase it a little bit differently. You need to make sure that you can build a solution and connect with both upstream and downstream chips. So you need to partner and test, not just with optical components as we've seen, but you need to test with semiconductors as well. So you have Leonet's in the room, you have IMEC in the room, you have other companies here as well, but there are companies that traditionally have built RF antennas, such as Wolfspeed is one and others. There are emerging, gallium nitride over silicon carbide that looks really promising, because those chips can handle high power, which is needed for those power amplifiers, and high frequencies. So those are just coming to the market. That's they were introduced in 2020. I don't know if there's any commercially available, but that would be a nice solution to partner with if it looks like it's appropriate for MIMO antennas. So key thing is to look at partnering and build a solution. You need to look at not just your optical component match upstream and downstream, but also semiconductor. But once they understand what you can offer, and it may take but once they understand, they'll be very interested in the solution that you can provide. So, but you've got to really reach out. It's not just about building your chip and say, I'm done. Here, I've got this wonderful chip. It's not enough. You need to build a solution. So make sure that you have upstream, downstream solutions, partners. They don't have to be within your company. They can be outside your company. And then also look at interfacing and working with semiconductor providers. And there's good news here too. There is an open call for indium phosphide PICs from JEPICs. So what they are now doing is you can apply until November of this year, and they will support 50% in-kind contributions. So basically you get a 50% reduction. You get support from experienced specialists. They cover design, manufacturing, and you can get more information at JEPICs.
And Tracy, if I can comment, well, thank you very much for introducing this slide about JEPICs. So if I can comment a little bit more, so JEPICs is a pilot line for going to large volumes for a pilot production of indium phosphide chips. So yes, I mean, it integrates all the supply chain. So it offers not only the production of the chips, but also they are going to provide to you PDKs, I mean, the design kits. So you are going to be able to design these kits and to fabricate these chips, and they are going to be compatible with other packaging offers. So yes, a good option if you are thinking about going to larger volumes of indium phosphide chips. Thank you.
Wonderful, excellent. Thank you, Anna. Thank you for adding to that. Okay, summary. We're on the home stretch here. Summary of factors fueling 5G new equipment buildouts. So we've hit all of these. There's nothing new. But keep in mind that as we talk about fueling 5G equipment, we're also talking about photonic buildouts. So we're looking at support of 5G cellular devices, the front-haul synchronization, the transition from CPRI to eCPRI, which requires timing, base stations synchronized with the front haul. with eCPRI. We're looking at installing highly accurate timing networks that will reduce our dependence upon GNSS and also the cost of a GNSS base station at each antenna. We're looking at providing accurate, 5G network synchronization for both hardwired connected equipment like switches and routers that are time-sensitive networks, as well as the replacement of non-time-sensitive network equipment. So all those existing Juniper, Cisco routers and switches, they have to be replaced. They cannot be upgraded. And if you're going to replace them at this point, you might as well upgrade the capacity. So there's opportunity there. So it's not just new stuff, it's complete replacement. And in addition to that, we have the replacement of Huawei equipment. We have the requirement for support of massive MIMO antennas, which include new fibers to the antenna. And also, we're looking at optical beamforming integrating into power amplifiers to better support massive MIMO and reduce some of the power requirements at those base stations. So lower power utilization solutions are important as long as you can provide the necessary solution that they need. Are you fast enough? Do you have the right density? And of course, optical components have that. So it's a natural fit. And we need also, when we're looking at replacing equipment, we need to keep an eye on higher capacities. So if you're going to take out and replace an old 4G system, you might as well increase the capacity because you're going to need it for 5G. If not immediately, you'll need it later. So we need for emerging applications, but we also need for the ones that will be coming in 2 to 3 years. And so there's an additional requirement to upgrade and install higher capacity fiber networks. So optical component opportunities, things that will be feeding the 5G surge include higher capacity silicon photonic transceivers, indium phosphide and silicon nitride, new radio area network components. So more good news for indium phosphide. PICs, we need more PICs. We need to have smaller packages that also use less power. Optical switch fabrics, especially on the switches and routers. Network fibers, including different types of fiber, multi-core, hollow core, and L-stab for timing. Long-haul transceivers, higher density transceivers, standardized co-packaging for interoperability. And please keep in mind that this is where we could lose. If we do not have standardized co-packaging that is developed now, you have co-packaging that has already been, or packaging solutions that have already been developed by Intel and others. And unless there is a standardized packaging that comes out now that can compete with theirs, we're going to have to assume the Intel or other developments that are already in place. So we absolutely need standardized co-packaging for interoperability. And then the other thing that's the big option or big opportunity for optical components is optical beamforming solutions that would be compatible with possibly new power amplifiers. So we've got lots of things that are hitting now. We don't have to wait for the applications, but you need to get out there and you need to talk to some of these carriers and equipment providers and develop your own solutions so that you're ready to go. You don't have 2 years. It needs to happen now. So, but there's lots of opportunities. This is a good thing. So with that good note, that positive note, I'd like to thank you so much. So for lasting this long and for your attention. And if you have any questions at this point, I'm going to turn this back over to Anna and take a breath. Anna?
Thank you very much, Tracy. It was a super interesting presentation, very nice market report. About questions, I know that this was not the goal for this market report, but maybe you have an idea of when we are talking about, for example, optical beamforming devices, which are the volumes that you could expect in the next 2-3 years?
You know, I can't tell you because I did not look at number of components, but I would anticipate that the market that would see the highest volume would be space. So, and then after space, I would see that there are great opportunities right now for interoperability with the power amplifier providers. So those would be the two main markets that I think I would focus on. So definitely talk to space, they're already doing it, but talk to what's happening, talk to the power amplifier providers here and see if you can work out a partnership.
Okay, so well, thank you very much, Tracy. If there are no more questions in the room, I would like to finish with this slide. I mean, I think this is what all the companies in the room were expecting, which are the opportunities, right, for photonics. I think you convinced them, so these companies are now going to look into this field. And well, that's it. Thank you very much, Tracy, also for, not only for this super interesting presentation, also for keeping it in 2 hours. It's amazing. And now if you want to continue the discussion, please join us in Wonder Me and we can ask more things to Tracy, okay? So thank you very much. Have a very nice day.